meet in orbit about the Earth. So, the goal here is to talk about the energy of a satellite in circular orbit about any object. We'll use the Earth. And then we're going to look at the energy required, the minimum energy required to go from one altitude to another. So, some equations that you're going to need. You know that centripetal force is MAC, which is this is the satellite, V squared over R, because it's the satellite that's in orbit. We also know that for anything in orbit, that for anything in orbit, that is provided by gravity. What else do we know? We know Newton's law of gravity, which is big G times the mass of one object, in this case a satellite, times the mass of the thing being orbited. I'm going to use the Earth just for the heck of it. It could be the Sun, it could be Jupiter, it could be anything that's being orbited, that mass, divided by R squared. The other equation we need, well, we need a couple of them. We know that E is the total energy of the satellite at any given point is its kinetic energy plus its potential energy. You know that kinetic energy is 1/2 mv squared. Again, this is for the satellite. And the potential energy is negative, and that negative sign has to be in there. It doesn't have to be here, but it has to be here. Negative mass of the satellite, mass of the Earth, or whatever it's being orbited. Oopsies, excuse me, I forgot the G. G times the mass of the satellite, mass of the Earth, all over R. Those are the equations we're going to need. Well, the energy of the satellite, as you already know, is equal to Ke plus Ug at whatever altitude we're at. So Ke is going to be 1/2 the mass of the satellite times its speed squared minus G times the mass of the satellite times the mass of what's being orbited all over R. So there's your equation. And you can go off and calculate this stuff without knowing anything else. We're going to go further, but you could go calculate these. You have the ability to calculate kinetic energy and the potential energy. Remember that R has to be in meters. You add the altitude in meters to the radius of the Earth, or whatever the radius of the object is itself that's being orbited. We also though need to figure out what is the speed of an object in orbit. And that is a circular motion question where you put the centripetal force equal to, which is in this case gravity, equal to mv squared over r, and you solve for v. I'll do that to the side. Again, the centripetal force is provided by gravity. So Fc is equal to Fg. Well, we know that that's big G times the mass of the satellite times the mass of the Earth all over r squared. And that equals mv squared over r. Again, the reason why it's the satellite, because it's the satellite that's going in a circle. Now, notice that the mass of the satellite is going to cancel. I've got it here and here. So the speed squared equals G times the mass of the satellite times the mass of the Earth divided by R, because I've got an R squared here and an R there, so that cancels with that. All right. I'm going to leave it as V squared. The reason why I'm going to leave it as V squared is because that's V squared. And I'm going to do a substitution. Now you can go off and calculate this and come up with an answer for the total energy of a satellite in circular orbit. But we can simplify this, believe it or not. It's going to look ugly, but the end result will be worth it. Oh, yeah. So this is going to be 1/2 times the mass of the satellite times v squared. I'm going to substitute all that in. Let's do 1/2 times the mass of the satellite. Oh, by the way, oops, I made a mistake. That cancels. Oh, bad teacher, because that canceled with that. So that gets canceled out. Okay, so I'm going to put in G in mass of the Earth times R. So G mass of the Earth all over R. Okay, that's minus G mass of the satellite, mass of the Earth all over R. Now, here's what's interesting. G, mass of the satellite, mass of the satellite, mass of the Earth, mass of the Earth, R. The only thing different is that that's minus a whole, and this is only a half. And just off to the side, if you have half of something, such as half of an x minus a whole x, like this is all x, what does that equal? It equals negative x over 2. You have negative half of an x, all right? That's what we end up here. So you end up with minus G, mass of the satellite, mass of the Earth, all over 2R. That is the equation for the total energy of any satellite in circular orbit. Again, if this were the sun, you'd put the mass of the sun in here. Whatever's being orbited. This is it. That is pretty cool. So how do you find the minimum energy to change orbit? Don't forget the negative sign. Again, that's part of the equation. How do you find that minimum energy? Now, you should be able to derive this. You should not memorize it. But that minimum energy would be the change in energy between the two altitudes. So that would be the final altitude minus the initial altitude. So we're going to do this twice. Minus G, mass of the satellite, mass of the Earth, all over 2RF, the final radius, minus a negative, because we got an awful lot of negative signs here. That's that negative. Minus negative, because negative is built into this. I ought to color code these differently. That negative's there. This negative is that one and that one. So minus G, mass of the satellite, mass of the Earth, all over 2RI. And when you rearrange this, you've got a lot of negative signs. If you distribute that negative here, that becomes positive, minus this. Notice that G, mass of the satellite, mass of the Earth, and 2, G, mass of the satellite, mass of the Earth, and 2, they're all common and they can factor out. This simplifies to G times the mass of the satellite times the mass of the Earth, all over 2, and then parentheses, 1 over RI, because remember that's negative to negative makes that positive. And then this is still negative here, minus 1 over RF. That's how you can calculate the change in energy, minimum change in energy of a satellite. And that includes its change in speed. So it's not only a change in potential energy, but a change in kinetic energy. Because where did the speed come from? Well, remember, here's kinetic energy. Right here. We've got both of those. And doing substitutions, that's how we came up with this. This combines both potential and kinetic energy in this right here. So this is the total change in energy, both kinetic and potential. Much easier than doing all of this separately. Ta-da!